Hi, what if I told you use multiplexers every day without even knowing it? I'm Quist, and today we are diving into one of the coolest building blocks in digital electronics, the 4 to 1 multiplexer, or you can say 4 by one MUX for short. But don't worry, this won't be one of those boring and complicated lesson videos you come across on YouTube. I am breaking it down brick by brick so that even if this is your first day in logic design, you walk away like a pro. So let's get started. So we asked ourselves, what's a multiplexer? A multiplexer is basically like a digital switch. Think of it like a smart traffic controller for binary data. Let's say you've got four data inputs, D0, D1, D2 and D3, but only one road is leading out. So the multiplexer decides which of the four inputs gets to take that road. That's where the select lines come in. You provide the multiplexer with two control signals, S1 and S0, and based on that combo, it chooses which inputs to pass through to the outputs. Simple, right?
To figure out how many select lines or control signals we need, there's a simple formula we use in digital logic, which is the base 2 logarithm of the number of inputs, where n is the total number of inputs, which is 4. So with a 4 by 1 multiplexer, 4 represents the number of inputs and 1 represents the number of outputs. Since we have 4 inputs, the value of n becomes 4, and base 2 logarithm of 4 becomes base 2 logarithm of 2 squared, which in turn becomes 2 log 2 squared equals 2. So the behavior of the 4 to 1 multiplexer can be precisely described using the Boolean expression, and it's what I'm about to take you guys through. So when the binary value of the select line S0 and S1 are both zeros, or you can say are both 10 of 0, 0, then it means that the selected input D0 an output of 1. So it can be expressed in a Boolean form. Y is equal to S0 is 0. So S0 becomes a complement, and then the other S12 becomes a complement, and then D0 is, since it's high, it is not a complement. So we move on to the next one. When S0 is 0, S1 is 1, then that means D0 is 1. So we're going to have S0 being a complement, and then S1 won't be a complement because it's high. 1 D1 plus we have S0 to be 1, so it's not a complement, and then S0 and then S1 and D2 continue. S0 not being a complement because it's this is a mistake here.
The extended truth table, providing a complete view of how the 4 to 1 multiplexer works. Over here we have the inputs of D0 to D3, and we have the select lines of S1 and S0. So now when X1 and S0 are both 0, then it means that we are selecting the inputs of D0. So when D0 is selected as an input, then it means that all the rest are 0. And it also means that the multiplexer sends D0 to the output. Now let's take another example. When the select line of S1 and S0 are known to be 0 and 1, just as we can see, then it means that we are selecting the inputs of D1. So D1 becomes high and the rest becomes low. Hence, D1 is passed to the outputs. This is the simplified truth table of the 4-to-1 multiplexer. As we can see, it is showing the binary values of the select lines S0 and S1, the binary values, and then they are directly mapped to the selection of one of the 4 data inputs of D0 to D3, which will also appear at the output. This is where we'll be building our 4-to-1 multiplexer using logically. I prefer logically because it's easy to understand and I recommend this for beginners. So if you're a beginner and you are into logic design and also you want to use this simulator just like I'm doing, then over here in the new tab, type logic.ly simulator and hit the enter button. When you click on this link, it redirects you to the simulator page and exit this to get started. We are going to build a 4-to-1 multiplexer, but this time we are not just dragging gates. We are going to build it straight from the Boolean expression or the truth table. Now commencing, we are first going to drop our 4 data inputs D0, D1, D2 and D3. Now these are the inputs, so we are going to look for it and label them so that we know which inputs we are using. Now we are going to need our 2 select line, S1 and S0, so we need 2 inputs and then give them a label each. Now we have them, but we'll have to rotate them so that they face downwards. So we are now going to need a NOT gate to get the inverted versions. So we drag 2 NOT gates. I'm just going to duplicate them. We'll make them face downwards and so since we have the NOT gates who will be given as the inverted versions, we are going to connect the wire from S1 to this NOT gate and S0 to this NOT gate so that we can have the inverted versions. But before we build our first set, let's not forget the AND gate, which we'll be using to connect the inputs. But we are going to need 4 of them, so I'll just duplicate them. It's our AND gates in series, but we'll have to increase the ports of each AND gate. I mean, each AND gate having a port of 3. Now we have our AND gates, we have the ports of the AND gates increased. Now we'll introduce an OR gate so that each AND gate can connect to the OR gate, but the OR gate just has 2 inputs, so we'll have to increase the ports to 4. And now we'll introduce the light bulb to be our output and give it a label as our output. So yeah, Now we have every component we need to build our 4-to-1 multiplexer. Now over here we have our Boolean expression and the truth table. So to build our first term of the Boolean expression, we have our select lines S1 and S0 to be both complements. So right here in the logic circuit, it means that S1 and S0 need to be in their inverted version when connecting it to the AND gates. Or you can go with the truth table and say S1 and S0 being 0, 0 means that S1 and S0 would have to be inverted when connecting to the AND gates. Now to begin with the connection, D0 will be connected to the first AND gate, and the inverted versions of select line S1 and S0 will be connected to the first AND gate as well. Now to build the second term of the Boolean expression, or taking the binary values of S1 and S0, which is known to be 0 and 1, then what we simply mean is the inverted version of select line S1 would be 0, so we connect it to the select line of S0 will be connected directly from its port to the second AND gate. So let's not forget that we have to connect D1 to the second AND gate. Same as applied to the rest. We refer them building the third term, which is S1 and then S0 complements, or 1 or 0 of the select line S1 and S0 to be and finally with the last term S1 and S0, which none of them is complements, or from the truth table, the binary values of select line X1 and S0 being 1 and 1, then it means that we are going to connect the select lines from their direct source to the last AND gate, and this. So yes, we are going to connect each AND gate to the OR gate. And connect the OR gate to the outputs. We are aligning the connections. So what we've built here is not just a circuit, it's a exact Boolean expression of the 4x1 multiplexer, physically wired as we can see in the simulator. So each term in the equation activates only when its select line combination matches, and only when one data input reaches the output at the time. The Boolean expression or the truth table, when the select lines of S1 and S0 are both turned off, which is 0, then it means that the input of D0 can only be turned on. When S1 is turned on, when S1 is 1 and S0 is 0, then it means that only D2 can be turned on. Or let's try S0 being 1, then it means that D1 can only be turned on. So this is how multiplexers control data in CPUs, memory buses, and even digital systems. But here's my challenge to you. Don't stop here. Try building an 8x1 multiplexer next, or maybe even design your own ALU control units from scratch. So if you enjoyed this lesson video, drop your questions in the comment section and I'll help you out. And also, if you've learned something today, Like, subscribe, and share this lesson video with that one friend who always gets confused in class.